It's just one number. And it's something small. They don't know what it is, but it's something small. The second thing to point out here is, like I was saying, now that I've now got highlighted in red, they transfer this idea of at some point to mean the place where the sequence enters that acceptable range. So to come back to our illustration, they were focusing on this problem of how close is close, introduced the idea of an acceptable range to resolve that, and that implicitly solved this other problem. So this is currently the state of affairs. They've got this solution, which is persisting in their discussion, and but they still have this other problematic issue that little n is fixed, partly because their acceptable range is fixed. So they again go to the board, they point out, okay, for this sequence, let's say this is our acceptable range, then this is the place for this sequence where it enters that range. All right, so this solution actually reinforces the idea, the fact that the acceptable range is fixed, reinforces the problematic issue that little n is fixed because the little n is attached to the acceptable range. It also introduces another problem, which the students, now notice I've labeled this as a problem, not a problematic issue, because the students focus on it immediately, and they end up wrestling with this for about an hour. And the idea here is that no matter what they make this, the size of this acceptable range, let's say they make it 0.25 zeros and a 1, it's still going to allow non-examples, things that aren't limits in, and that's bothering them, but they don't know how to resolve that. And then Craig told you that I was going to show you an instance where we play the role of a solution provider. So that's this yellow thing over here. And what we do is we don't provide a solution in the sense of telling them to use the idea for every epsilon. In fact, the students generate the idea of using for every epsilon and talk about it very coherently. The problem is that they didn't raise that idea of for every epsilon in the context of wrestling with the problem that's down here below, that one epsilon allows non-limits. That it came up in a separate conversation. So the role that we played as a solution provider was actually the solution of bringing these two things together into a single conversation where they could see this as resolving the problem. And that's going to implicitly resolve the problematic issue of little n being fixed. So the students observe several positive aspects of the acceptable range, but they also notice several problems with it. For example, its size is arbitrary. It's not well chosen. They like their idea of decreasing errors because it captured the intuitive notion of getting closer. And different numbers that you might use for epsilon create different definitions. They say that I might define it one way and you could define it some other way just because you're choosing different things. And I'll point out these last two things here, or the one size doesn't eliminate all limits is the problem that I mentioned in the previous slide. And then they also were concerned that it allows graph E to converge. So here's graph E. This is the damped oscillation. And in the process of thinking about this, Megan makes this comment. She says, because it will eventually get within whatever range we want to put it in, though. Whether it's 0.25 zeros and a 1 or 1,000 zeros and a 1, it will get within that range and it will stay there. So here is, in fact, a beautiful articulation of the idea of the formal definition. It's framed in informal language, but it's perfect. It's got the universal quantification of the epsilon in particular. But Megan, when she said this, wasn't focused on the problem of eliminating non-limits. And so they wrestled with this for over an hour. And at that point, the interviewer suggested that they consider the idea of using for every error. They were talking about errors here instead of epsilons, but they eventually changed this to epsilons. And then they both kind of look at each other, and then they jump on it. They talk about why it would work. They go up to the board and they talk about the different sizes of epsilon and how that played out for the different graphs, and then they incorporated it into their next definition, and then it stuck. It was in almost every single definition after that. So it was a very persistent solution as well. So this is what Craig meant when he said that when we provided solutions, we tried to do so in a way that was with a strong consideration toward appropriate timing. And these students had wrestled with the problem, so they were really familiar with what the nature of the problem was, and they had previously talked about the things that they needed for the solution, and that they immediately seized on that, and that it persisted was or were kind of indications that they were really ready for it. And with that, I'll turn it over to Craig, and he'll take you through a few more things.
Okay, so we're going back in time a little bit here. Mike talked about the progress that the students made from their third definition that you see there to resolving the two issues raised below, the two bottom ones there. And I'm going to say a little bit about how the students resolved the other two problematic issues, that being that for a while there, little n, was referring to multiple things, both the fixed point on the n-axis beyond which certain behavior happened. That was one issue, it was referring to that and all the indices on the terms of the sequence. And also, their other issue that they didn't realize they had was how are they going to refer to the terms of the sequence that they really care about, that is, those terms that are after that point n. And you see there in their third definition that they're referring to them as a sub n plus 1. And that would eventually become something they needed to resolve. So we'll focus on these two right here. And as you can imagine, for the students to be able to distinguish the terms of the sequence, the a sub n's that they care about, in other words, the ones that are after that some point n, one of the things they're going to have to do first is to come up with different ways to notate the thing on the n-axis that's fixed and the terms of the sequence, or the indices of the sequence. So the first thing they need to do is address the problematic issue that you see on the left-hand side there. And so what was going to need to happen first is that this is going to need to actually become a problem for them. Right now is just a problematic issue. And I'll tell you a little bit about how they eventually got to their explicit solution of calling that fixed place on the n-axis a cap n. So there we were on the second day, and one of their more recent definitions there said a sequence converges to 5 as n approaches infinity only if there exists a value little n after which the 5 minus a sub n, an absolute value, the error there, does not exceed your chosen error and the size of the errors decrease. So this just gives you a snapshot of where they were at about the middle of day 2. And at this point they still were using little n to refer to multiple things. So I said, well, my question was this 5 minus a sub n, what does a sub n refer to? And the reason I'm asking is because it occurs to me that we're using n to mean, given some error, a static place here, right? And I was pointing at a graph up on the board, and Megan and Belinda agree, and I said, and then this n also refers to a whole bunch of points. Megan agrees, and so I said, could it clear up confusion to call one of them something else maybe? And then God intervened, and Belinda picked up a pen and said, maybe we could call this thing Big N. And I smiled a big smile and thought, wow, that couldn't have gone any better. And she replaced the little n with a cap n on their graph. So just to check in with you folks, what best describes the role that I played in the previous slide as we were having the conversation? And I think we should have a pop-up poll coming for you here in a minute, so you can think about those 4 different roles and what best describes the role that I played. Okay, so you'll notice that we have responses for all four, and actually that's accurate. We really, the role I was playing in that previous slide, and I'll go back to it here so you guys can take a look, was really all four in some sense. Because I was certainly guiding the process in the sense that the students had kind of reached a point where this is going to become an issue they needed to deal with if we were going to make progress. And so I was guiding the ship towards productive waters in the sense that I was raising their attention to something. And you'll notice in my first question there at the top of the slide, and then my second comment, I'm playing the role of a conflict producer there, because I'm bringing to their attention this issue that exists that they were unaware of. And really, that last question where I say, could it clear up confusion to call one of them something else, I really was acting in some sense kind of like a solution provider. I wasn't full on providing them the solution in the manner that Mike had talked about earlier when he talked about one of the other interviewers saying, what about for every error? So you'll notice I don't come out here and say, hey, what about calling this thing cap N? But that question there right before Belinda suggests a cap N kind of leads them in that direction, for sure. Let's see. Yeah, I was a catalyst provider. That's a good way to put it. So let's see. April asks if I could talk a little bit about how to make problems arise from problematic issues. So I think that's really just a process of just asking the kind of question that might lead them to recognize there's an issue in their definition, and specifically what that issue is. So for instance, if a student was to say something like, the errors will always get smaller or will always get closer to the value of 5, maybe asking them to apply that definition to one of the graphs they came up with, which was the oscillating dampening graph, and that might lead them to recognize there's a problem with their definition. Does that help? Okay, so moving on. It's worth pointing out, that Belinda had introduced this big N and she wrote it on the board, which was great, right on their graph. And subsequent to that, we said, okay, why don't you capture this idea in a new definition? And so right away they sat down and they essentially replaced the definition they had previously that had a little n with a cap N. And one of the things that was kind of interesting is from that point on, because this really was a solution to a problem for them, and it wasn't a problem for very long. You'll notice it had been a problematic issue. We raised their attention to it. It became something that they were aware of that they needed to fix and that they provided the solution for, and then that solution really stuck. So from here on out, that cap N was in their subsequent definitions. So this one problematic issue had been resolved, and we still had the other issue, though, of how are they going to refer to the terms after that sum point cap N. And so I'm going to tell you a little bit about how that came to be. First of all, if I go back there just a second, you'll notice that this at some point little n is now an at some point cap N, which is nice. And the other issue that we needed to resolve was which